Said you just want to do part C? Okay. So it's if you haven't done the homework, and I should go by and see who has and hasn't, but I just don't want to be disappointed any more than I already am with my other classes. So I'll let you guys stay part of my happy memories. But I did this in mechanics the other day before yesterday. Checked to see how many of them done their homework, and it was less than 50%. So that was a rough day. So we have some marks here, and they've shaded this area. Something like that. All right, so I think this is they also say that this is the positive x direction. All right. It says a spring launcher on level ground is retracted a distance minus d from its equilibrium position. So this is the relaxed position of the spring. So the box has been pulled back a distance negative d. It is used to launch a small box of mass m. There's a coefficient of friction of mu between the ground and the box beginning at 0 as shown. So over here there is friction, but there's no friction over on this side. If the spring is actually pulled back a distance of 2d, find an expression for the actual distance to where the box comes to rest in terms of d. So I think what is indicated, and I didn't read all of it, but when you pull the box back to negative d and release it, the box stops when it makes it to 3d. Those are the original conditions of the problem. Does that make sense? All right. And we know we have this coefficient of friction mu here, and they're trying to ask us what will happen to the system if we pull it back twice as far. Well, we know it's going to have twice as much energy in the system. Does that make sense to all of you? Yes? No? Okay, twice as much energy in the system. So that energy has to be bled out by friction. Now, you may jump to the answer like, well, it's probably going to be 6d, right? Twice as far has twice as much energy. But does it really have twice as much energy if you pull it back twice as far? That's the real issue. If you look at the original amount of elastic potential energy we had, it's 1/2 k d squared. But in this new circumstance, it's going to be 1/2 k 2d squared. Well, let's compare that to the original amount of energy then that we have. We've done this a little bit before, so let's kind of get an idea. We've got a change. I want to see how this change affects our total amount of energy. So I'm going to square what's in the parentheses there, and I'll get 1/2 times k times 4 times d squared. Now if I rearrange this, I'll get 4 times 1/2 k d squared. That suggests I don't have twice as much energy when I pull it back twice as far, but I have 4 times the energy. Does that make sense? Now the work done has to be to get rid of that energy. So I'm going to put something else in front of you. Net work equals the change in kinetic energy. I'm doing that because when we launch this box, the box makes it to here with all kinetic energy. Agreed? But then that kinetic energy is taken to 0 by friction. Now the only force acting on the box when it's out here is the frictional force. Is the frictional force affected by how much energy the box has? Meaning, does friction change because the energy of the box is greater? No. If you don't know why I'm asking that question, that's one thing. But if you don't know the answer to that question, that's something entirely different. You should be aware that friction is equal to mu times the normal force. And in this case, the normal force equals mg. Did any of this change just because I pulled the box back further? No. So the frictional force is going to be the same. And that suggests that the only force doing work is friction times the displacement times the cosine of 180 degrees. I'm bringing this up because if this stays the same and this stays the same, But this is 4 times greater, then this will have to be 4 times greater. So is it going to land at 3D? No, it's going to land at 12D because it's going to have 4 times more energy, so it's going to travel 4 times further. I'd say that's a challenging question. Is it unreasonable to expect you guys to do this? Well, College Board doesn't think so. Now, maybe unreasonable with the amount of work we've put into this particular unit, but we're going to have to get there. Fair enough? All right. Is that a reasonable explanation? Welcome. In this problem, they say that they take the hammer, lift it up 1 meter above the nail. When they release it, the nail gets pushed in a tiny amount, 0.5 centimeter. That's not very far, so I don't think I really need to add that as part of the distance the hammer falls because it's so small compared to the distance the hammer was pulled up. Does that make sense? We can, but I think we can get to the point of this without having to do that. So we start here, and then we end with the hammer and nail a little bit in. Does that make sense? What kind of energy does a hammer have when it's pulled up above the nail? Yeah, it just has gravitational potential energy. It does not have either of these. Now, just before it hits the nail, like right here, so it's just right about to touch the nail, but it hasn't hit the nail yet, what kind of energy does it have? It has kinetic. Now, when it hits the nail does work on the hammer, right? The nail applies an upward force on the hammer, and that upward force does work on the hammer, taking away the hammer's kinetic energy. Would you agree? Would you also agree then that by Newton's third law, the nail must have also had work done on it, right? A force on the nail that changed pushed the nail into the ground a little bit. Does that make sense? Well, the energy the hammer starts with has to be the energy the hammer finishes with right before it hits the nail, which has to end up being the work done on the nail. Does that make sense? I mean, the energy has to stay the same. So if I can figure out how much energy the hammer started with, that has to be the amount of energy delivered to the nail. This assumes the person didn't push down on the hammer. Right? We're assuming that the hammer just fell naturally and hit the nail. And I think they say that in the problem. If they don't, we're going to have to assume that because we don't know. It says, what is the potential energy? Yeah, so we're going to have to assume that the person didn't push down on it and adding more energy to the hammer. So I think we're just going to do mg h minus h naught. But in doing this, I'm going to, again, make some general decisions here. Like I'm going to make I'll make this our reference point. If you want to make it a meter plus 0.5 centimeter, okay, but that's not very far. So I'm just going to make it a meter. So that just means we have a 2 kilogram hammer times 10 times 1, or 20 joules of energy was with the hammer, and I think the 20 joules of energy was delivered to the nail. Now it says, what was the average force applied to the nail from the hammer? Now that question I think has some good stuff in it. That work done is equal to 20 joules. Would you agree? But that work was the force on the nail times the displacement of the nail times the cosine of 0 degrees, because the force was down and the nail went downwards, and that has to equal 20 joules. The displacement of the nail is 0.5 centimeter. So 0.005 meters. So the force on the nail, 20 divided by 0.005, so 4,000 newtons of force on the nail. Is that okay? Not too tough, but there's stuff here. How much work was done on the hammer by the nail? 20 joules. Right? Stop the hammer. So I think we've already handled that question too. That all make reasonable sense? All right, so in question 2, we have a hammer. And one of the things that I don't know if you've noticed I tend to do with these questions is I tend to try and break these problems up into stages. And I think it would help you if you did the same. So I kind of see 3 stages with this question. There's the stage where the hammer has been lifted 1 meter above the nail. There's the stage where the hammer has dropped, bless you, 1 meter and is about to strike the nail and is moving downwards, but hasn't started pushing on the nail yet. Does that make sense? So it's moving, but then there's the state of the problem where the nail has moved a small distance, 0.5 centimeters, and the hammer has come to rest. I think breaking these problems up into parts is important. When the hammer falls, energy is conserved. So when you lifted the hammer up and brought it to this height, you did work lifting the hammer. But now that you did that, what kind of energy does the hammer have? Sure, it has gravitational potential. The hammer falls, and just before it strikes the nail, what kind of energy does the hammer have? Kinetic. I think the fact that the nail moves just a small amount means I really don't have to worry about that little change in distance. Like I don't have to, when I'm setting the reference level, I don't think I have to include the half centimeter. Do you guys agree? I mean, half centimeters is that much compared to how high the hammer was lifted, which was this much. So I think as a reference level for energy, we could probably use that as the reference level. Would you guys agree? All right. Now, you specifically wanted me to talk about question D, which the hammer comes to rest against the nail. It does not bounce. The nail is pushed into the wood 0.5 centimeters. How much work was done on the nail? No. Just remember, work is the method by which you change something's energy, right? Also, Newton's third law. The hammer does work on the nail, and the nail does work on the hammer. And it has to be an equal amount of work. So whatever work the nail did on the hammer is the same as the hammer did on the nail. Well, the hammer has mgh minus h naught amount of energy. This is the work you did lifting up the hammer. And a hammer is 2 kilograms in a gravitational field with 10 meters per second squared of acceleration and is 1 meter above the nail. That's a total of 20 joules of energy. All good? How many joules of kinetic energy does the hammer have just before it strikes the nail? It's got to be 20, right? The energy at the top has to equal the energy at the bottom, so 20 joules of energy. Now, the hammer is going to do work on the nail, but at the same time, the nail does work on the hammer. The work done on the hammer has to change the kinetic energy of the hammer. What's the final kinetic energy of the hammer after it comes to rest? Zero. The hammer's not moving anymore, right? And it's all the way down at its lowest spot. So when a hammer comes to rest, its final kinetic energy is 0. Its initial kinetic energy was 20 joules. That suggests minus 20 joules of work was done on the hammer. Do you follow what I'm doing? Look, it's the flow of energy, guys. So the hammer had 20 joules of energy. It gave that 20 joules of energy to the nail in driving the nail in. So how much work was done on the nail? 20 joules. If the nail did negative 20 joules to the hammer had to do positive 20 joules to the nail. You guys follow that argument? I know that this, after having done Unit 2, which is really hard, with all the force diagrams and vectors and trig and stuff, you probably feel like you're second guessing yourself a lot here. But this is quite literally what we're doing here. We're following the flow of energy. So in any system that has energy, it has to go somewhere. So you did work lifting the hammer up. Gravity brought the hammer back down, and because it's a conservative force, the hammer retained the energy, which is why it was 20 joules here and 20 joules here. The hammer is stopped by the nail, so the nail took away the hammer's 20 joules of energy. What gained that energy? The nail. And then, of course, the nail promptly lost that energy, didn't it? Probably heat, breaking the piece of wood it's going into, stuff like that. That energy got dissipated because when we're all done, the nail's not moving either. But the hammer delivered the energy to the nail. That's the answer to question D. Do you want me to keep going? Okay. So we want to know how much force the hammer applied to the nail. Well, remember the hammer's doing work on the nail. It does 20 joules of work. That work has to be the force times the displacement times the cosine of 0 degrees. The hammer pushed down, the nail went down, so the angle is 0 between the pushing force and the direction the nail went. Agreed? And do we know how far the nail went while the hammer was hitting it? 0.5 centimeters. So the force of the hammer times the displacement of the nail, which I need to convert to meters. So that's why it's 0.5 centimeters, 0.005 meters equals 20 joules. So just figure out the force. I find the force has to be 4,000 newtons. So it pushes down a lot. I don't want to get hit by a hammer. Go ahead.
Could you do the work over like the distance that the nail traveled down to find?
Well, I need the force, right? So to find, and the definition of work is force times displacement times the angle. So if I want to isolate force, which is what I'm doing, I take the energy, the 20, and I divide by the displacement. I mean, that's where I get the 4,000 from. I'm not sure I'm answering your question or not. Yeah. Oh, sorry, go ahead.
I did a little different. I did the work, and then I just divided it by the distance that the object traveling. I still got 4,000.
Well, that's what I did. This is the work. This is the 20 joules of work.
Could you do that like in every scenario, or just?
I don't know if I can say you can do it in every scenario. But this scenario works. But again, if you know how much work is done, that has to equal force times displacement times the cosine of the angle. So assuming that things are the same here, that the force is in the same direction as the displacement, you can make many of those same kinds of parallels to whatever problem you're applying it to. All right?
But the angle is 0 in this case, like when would it not be 0?
Well, the work done on the hammer, the angle isn't 0. Right? The force on the hammer is upwards, but the direction that the hammer goes is downwards. So in that case, the angle would be 180 degrees. That's why negative work is being done on the hammer, because it's stopping the hammer. But also, like the example I did at the very beginning of the unit where I pulled the chair at an angle. If I pull the chair at an angle, that's going to be applying a force at an angle, so only a part of that force is doing work. The other part of that force is lifting the chair or something like that. Does that make sense? So you can pull it any direction. The thing that I want to emphasize to you, and I guess to the class, is that the only part of a force that can do work is a part that's either in the direction of motion or against the direction of motion. So, if we consider a problem like this, where you take and pull on a box with a force this direction, and the box goes across the floor? Well, there's lots of forces acting on the box. There's obviously the applied force, there's a normal force, there's weight, there's likely friction, right? All these forces are acting on the box. But not all of them are doing work, right? This force is doing work because it has a part of the force in the direction of motion. The whole thing isn't doing work, only a part of it. That's why we have to find this angle and multiply by the cosine of it. That tells me how much of this force is doing work. The other part of that force is pulling up on the box. That's not doing work. The normal force isn't doing any work on the box because it has no component in the direction of motion. And the weight isn't doing any work on the box because it too has no component in the direction of motion. Now, friction is doing work on the box, but it's doing negative work on the box. It's acting against the direction of motion. So although this force is trying to give the box energy, this force is trying to take it away. Does that make sense? Okay. All right. Okay, it says a small cart of mass m is located at the bottom of a hill of height 4h, as shown in the diagram above. So it says that we have a velocity v here. Find an expression for the minimum speed of the cart in order to make it to the top of the hill. This is a conditional problem, and one of the things I try to remind you guys about when it comes to conditional problems is how do you set up a conditional problem? If I push the car hard enough, when it makes it up here, it's clearly going to have gravitational potential energy because it's above its reference level. Now, the faster I push it, assuming it doesn't leave the track, the more likely it's going to have a bunch of kinetic energy when it makes it up there too, correct? Does that make sense to you? Because the car will be moving and will be higher than it started. Down here, it has all just kinetic energy. Now, these two things are equal. Back to this problem. Enough of that. So we want to find an expression for the minimum speed of the car in order to make it top of the first hill. So I'm looking right here at this. You know that as I make this smaller, look, this is a fixed amount, right? That's based on how high you are above the reference level. So before we even go with this, that's going to be mg times 4h. To get up there, you have to have that amount of energy. Any extra energy will be in kinetic. So if I want to find out the minimum speed, I want to reduce the starting amount of kinetic energy until this energy disappears. Does that make sense? That makes it my minimum. That's what we mean by threshold values. We're looking for things that are at the edge. I can push it harder than this. I can give it more kinetic energy. It just means that it'll go over the hill. But I want to provide it just enough to make it to the top of the hill and stop. Does that make sense? All right, that's what we're going to do then. So this will be my 1/2 mv minimum squared. And that equals mg times 4h. And cancel the m's, multiply both sides by 2, take the square root, and we'll get v minimum equals the square root of 8gh. So I can push it a little harder than that. If I push it with less of this velocity, you understand it won't make it to the top of the hill and will roll back. Does that make sense? You guys ever seen those stupid carnival games? We have to roll the thing over the, I don't know, do they still do those at like carnivals? Take your money away? Mostly because if you don't look carefully, you'll notice the table's actually slanted. They do that kind of stuff to try and cheat you out of your money. It's on purpose. They're going to win. They will. You're going to Busch Gardens, some of you tomorrow. Question B. The spring, a spring constant K, is located on a landing on the opposite side of the hill. What is the speed of the car just as it makes it to the spring, assuming that it successfully made it over the hill? So I think we're still talking about having this same amount of energy, right? We just made it just barely to the top, and then it rolls down the other side. Is that okay? So we're not really adding any more energy. We're talking about this minimum amount of energy. Is that good for you guys? Well, that suggests that the energy that we have is still going to be mg times 4h. That hasn't changed yet. That's still the energy that's in the system. But now that we're here at this position, we will have gravitational potential, and some kinetic. And they're asking us to figure out how fast the car is going. I think we can get that from this. Is that good for you guys? So we'll do that work over here. I'll have mg times 4h. That's the amount of energy we start with. And that has to equal, we are 3h high, so mg times 3h plus 1/2 mv squared. So this is just going to be, I cancel out the m's, subtract both sides. I'll get mgh equals 1/2 mv squared. I didn't cancel the m's, so now we'll cancel the m's out. Multiply by 2, divide by v, or I'm sorry, take the square root, and I'll get the square root of 2gh. That's how fast it's going right when it hits the spring. All good? Excellent. What is the maximum compression of the spring in terms of all those things? Okay, well, the maximum compression of the spring will be when the car stops. Agreed? So I don't have to redraw the picture. You guys can use your imaginations, and that's okay. So I think we'd have the situation where we still have mg times 4h as our total amount of energy, but now we have mg times 3h. There's still that much potential energy. We're still at the same height. And I could have reset the reference level, but we already have this, so I thought we'd just keep going with it, if that's okay with you guys. Plus 1/2 k delta x squared. All good? So I subtract both sides, mg times 3h from both sides, get 1/2 k delta x squared equals mgh. And I can't cancel out the m's this time, so we're just solving for delta x, and we'll get 2mgh over k. I'm going to take the square root. Can you see it better now? It's right up there. Whose head's in the way? Is it better now? How about over here? Good. Glad. Moving on. This time, the car begins its run from the spring, and the spring is pulled back far enough for the car to make it over the hill. The hill, however, is circular with a radius of curvature of h. What is the maximum speed the car can successfully make it over the hill and not lose contact with the ground? And then what is the speed of the compression of the spring to make sure that it stays on the track? That's an excellent question. And I know this is where you guys will probably come off the rails a bit. So if you've been waiting for this question, good, because I think you should be able to do it. Like if I was giving a test today, this is okay and fair game. Everybody understand? Because I think this is where some of you guys will start to fall apart. So this is a new question, really. We don't have to deal with any of this old stuff if we don't want. So I'm gonna clean the problem up so we can start fresh. All right. So this time we are dealing with a different threshold, a threshold set by the fact that there is a radius of curvature here of the hill of h. I get that it's not drawn to scale, but this will be okay, right? These problems are force problems, if you'll recall. The car leaves the track under certain conditions. And the condition here is when the normal force goes to 0. So let's remember how this problem is set up. The car successfully negotiates a circular track if the unbalanced force acting on the cart is equal to MAC. This is one of those places where you guys tend to have issues. So I want to remind you, this is a force problem. How do I know the difference? Circular motion. They tell me about the fact that it's a circular track. The moment they said circular track, I knew this was a net force problem. If you're trying to figure out how to negotiate questions, you got to begin to realize that there's clues that lead you to which one of our units you're being spoken to about. When we're talking about problems that deal with velocity, changes in height, springs, that's all going to be conservation of energy. But the moment this problem switched to asking you about the circular motion of the car, it became a net force problem. That's how you know. Circular motion is a centripetal acceleration problem that requires a specific kind of force and a certain amount of force for it to work. There are two forces acting on the car here. There's a normal force upwards and the weight of the car downwards. The unbalanced force has to be towards the center, which means net force, well, let me back that up so I have more room. Net force equals mg minus normal force, and that has to equal mv squared over r. I am making downwards positive because that's the direction of the acceleration. I have to have an acceleration downwards in order to go over the circular path. Now, look, if v is small, maybe if v is 0, the normal force just equals the weight. Does that make sense? I don't know how your brains work on this. So I want you to watch this for a minute. And I'm just going to kind of go over to the side here to do this. mg minus normal force equals mv squared over r. So I could write this as mg equals normal force plus mv squared over r. Now, I wrote this purposely. The radius of curvature of the track doesn't change. It's a constant, right? The track is made. It's already there. The mass of the car isn't changing. It's a constant. It's something that's about the car. And g doesn't change. It's a constant. But n and v can change, right? It depends on how much I pull the spring back determines what v is. And clearly there's a link between these two. Do you see that? They have to equal something that is a constant. That number can't change. So if this number goes up, this number has to go down. Do you see what I'm saying? When it was on the other side and I was subtracting it, I think some of you had trouble. So I put them both on the same side. These two numbers have to add up to be this. Have to. No more, no less. But the normal force can change and the velocity can change. So if I make the velocity smaller, the smallest the velocity can be is 0, right? So if the velocity is 0, this whole term goes away and the weight equals a normal force. Yeah, because it's just sitting there. But the moment it starts to move, the moment v has any value other than 0, then the normal force has to diminish. What's the smallest the normal force can be? Can it ever be negative? Can it ever pull down on the car? It's not a roller coaster. So the smallest it can get to is 0. 0 is the threshold. So that's what this problem is about. When the normal force goes to 0, we are at the threshold. This is the minimum speed. I'm sorry, not minimum. It's the maximum speed. Maximum speed. If it goes any faster, then it loses contact with the track. So cancel the m's out. And V max equals GR. I can't go any faster than that or else it shoots off the track. Oh, I forgot the square root sign. There we go. Now that sets us up for the next part of the problem. We cannot be going faster than this speed. So they want us to figure out how far can I pull the spring back so that I don't shoot the car off the track. Clearly, if I pull the spring back farther, the car will be going faster, right? So we want to find out how much do I pull the spring back and not exceed this. So let's look at what we have over here. Go back to our problem. When I pull the spring back, and are you okay if I reset the reference level to be here? Is that okay with all of you? Or do you want me to leave the reference level at the bottom? It makes no difference to me. It won't hurt my feelings either way. I don't care. So this is good? Leave it at the bottom? Okay. So if I leave it at the bottom, when I pull the spring back, I'm going to have gravitational potential energy because I'm above the threshold or reference level, and I'm going to have elastic potential energy. And when I shoot the car up and it makes it to the top of that ramp, it's going to have gravitational potential energy. But there is a max amount of kinetic energy it can have. You can't have any more than this. All good? So let's figure out what this maximum is. This will be mg times 3h. this is going to be 1/2 k delta x max squared equals mg times 4h plus 1/2 mv squared, v max squared. Now, I'm going to write it in here because some of you need an extra step. But we know what v max is, right? We just solved for v max a minute ago. And we found that v max was the square root of gh, right? Did we put r over there? We did, but r is h. Do you remember that in the problem? Okay, so stupid me, I should have known that. All right, so gh, there we go. I'm going to substitute and do arithmetic for you. So let's see, I bring my mg3h over and I get 1/2 k delta x max squared equals mgh plus 1/2 m. v max squared is just gh. I substituted it in and placed it here. Everybody okay? Everybody see what I did? mgh and 1/2 mgh is 3/2 mgh. I just added those two numbers together. 1 plus 1/2 is 3/2. If you don't like fractions, then make it 1 plus 0.5 and get 1.5. And then the other side is still 1/2 k delta x max squared. I can get rid of the 2's. I multiply both sides by 2 and that gets rid of it. And divide by k. So delta x max squared equals 3 mgh over k. I just take the square root now, but that's my answer. A lot of writing going on. Conversation we've had, the idea here is that if I pull the spring back this amount, the car will just make it over but won't jump. If I pull it back further, the car jumps, right? It loses contact with the track and goes airborne. You know there's a minimum amount too. Do you understand that? That if I don't pull the spring back enough, the car won't even make it to the top of the track. Have you found out what that number is? Because we could. And I think we should. Because there's a range. If you pull the spring back not enough, the car just goes partway up the hill and comes back. And if you pull it too much, the car jumps. So there's a range that's going to be okay. Let's find the range. Let's find the minimum necessary to make it to the top of the ramp. Everybody got it? Can you do that on your own? Can you try? Because that would be my new follow-up question. That's what I would probably put on a test if I were putting this on a test. What is the minimum? We found the maximum. What is the minimum? Try it. It's not hard. Okay, so let's tuck this away, what we have right here, because we want to compare this to the answer in a few minutes, right? So I'm just going to kind of tuck it away someplace where we can come back to it. And I'm going to get rid of all the stuff that's here because we don't need it. Well, I didn't mean to get rid of the track, but that's done now, so. Okay. All right, so without redrawing everything, we're going to pull this back and we're going to shoot the car so that it goes to the top of the track. At the top of the track, it can have two kinds of energy, gravitational and kinetic. At the spring, it can have two kinds of energy, elastic and gravitational. Right? The gravitational in both of these is a fixed amount because we are the same height both times. So it's mg3h for where the spring is, and it's mg4h where the top of the hill is. Right, so this is our situation. So we can pull the spring back, and it needs a certain amount of energy to make it to the top of the hill, whatever the difference is between these two. Any more energy that it has goes into kinetic. Does that make sense? Now, the minimum amount, again, is the amount to just make it to the top of the hill. So if I pull the spring back less and less, K becomes smaller and smaller. What's the smallest it can be? 0. So let's make it 0. That makes this the minimum. I need to at least pull it back this far. If I don't pull it back this far, the car will not make it to the top of that ramp. So let's figure out what that is. I'm going to subtract the mg3h from both sides and get 1/2 k delta x minimum squared equals mgh. I'm going to multiply both sides by 2 and divide by k. So delta x minimum equals 2mgh divided by k. And yeah, I'll take the square root too. All good here? Let's compare it to what we had for the maximum. It is nice to know that if I take the square root here for the maximum, the number I have here is bigger, right? 3 mgh over k versus 2 mgh over k. But that's a pretty narrow range, isn't it? There's just a small amount in there between it doesn't make it up or it goes too fast and flies off. Not a great toy if you're trying to design it for kids, by the way. Although the kids probably like to see the car jump all over the place. I don't care. But again, this is kind of what we're talking about with this range. Look at the things that determine this, because this is the follow-up. This is like, I answer this question with a couple of words. Like, does it make sense that m is in the numerator here? Do you see why it's in, like, if the car were heavier, we'd have to pull the spring back more. Does that make sense? Because m's in the numerator, obviously, but the car's heavier, it has more inertia, it's harder to push. So it'll take more effort from the spring. Does that make sense? Does it make sense that h is there too? Because if h is bigger, it's going to be higher. So it's going to take more energy from the spring to get it up there, right? That makes sense. Does it make sense that k is in the denominator? So I think you guys don't have a good idea of what k is about. But k is the strength of the spring. So a stronger spring will hold more energy with less pullback. So if k is bigger, I get more energy in the spring without pulling it back as far. Does it make sense that it's in the denominator then? Because if it's in the denominator, it makes the delta x smaller if k gets bigger. So if I use a stronger spring, I don't have to pull back as much. Again, if you're designing a kid's toy, you may want to choose a spring that is soft enough that the kid can operate, but strong enough that you don't have to make the whole thing very big. Right? You don't have to pull the car back very far. Stuff like that. I'm going to change this problem a little bit because there's some things in this problem I think that if I was rewriting it, I would do differently now. This problem I gave on a test a couple years ago, so it's been, once I've used it enough, it goes into the homework sometimes, so that's where really it came from. It's modeled on a problem that was on a multiple choice test years ago, and then I saw on an FRQ, so this is not a particularly unique question. It's often in textbooks and stuff because it has all the basic 3 kinds of mechanical energy that we talk about. But there are some things I would change if I was asking you guys to do it, and I'll talk to you a little bit about what those things are. So question A, it says find an expression for the minimum speed of the cart in order to make it to the top of the first hill. We actually did that part yesterday. Do you guys remember that? And we found out that minimum speed to make it to the top of the first hill was the square root of 8gh, right? So question B, the spring of spring constant K is located on the landing on the opposite side of the hill. What is the speed of the car just as it makes it to the spring? So this question is not about the spring, but is about the speed of the car here just before it contacts the spring. So it's still moving here. Does that make sense? Now, what's that? We sure can. Now, if it were me, and you're trying to figure out, well, is this going to be an energy question or not? I think this is still an energy question. There's a lot of reasons why I think it's an energy question. Like I said to you guys, I was going to try and tell you how I would know which thing to use here. And we used energy to figure out, how fast the car had to go to get up here because we set the kinetic energy here equal to the gravitational potential energy here. And one of the things I think I tried to say to you guys yesterday is that, look, if the kinetic energy here at the bottom, which I'll put right here, is greater than the gravitational potential energy here at the top, that extra energy would just go into kinetic energy at the top, and that would be where all the energy goes. There's these stupid little graphs I don't usually teach with, but they're like energy graphs and have U, and K. So elastic, gravitational, and kinetic. At the bottom, it's a bar graph, and this is all the energy is in the form of, let me do this different. All the energy is in the form of kinetic at the bottom, right? So make a little bar there. But then if we take the same thing and, consider what it is over at the other side, well, when it goes to the other side, up here, that bar graph, which is still U, E, U, G, and K, well, it's going to have less kinetic energy, and it's going to have more gravitational potential energy, right? But these two things here still have to add up to be that. Does that make sense? So I don't do the bar graph thing, so maybe the bar graph works for you. Maybe it helps you understand what's going on here. I put it in the cheat sheet for you guys to kind of see it, but I don't usually use it much in my teaching. So with that, it's talking about wanting the minimum speed necessary, and that's how we got to this idea that if the K on this side gets smaller, the K on this side gets smaller because the amount of energy we have up here at the top has got to be mg times 4h. That's how you get to the top of the hill, right? So the minimum amount is when we make it to the top of the hill and have no kinetic energy. Does that make sense? That was from yesterday? But now that we've done that part of the problem, look, we're at the top of the hill. So I'm going to say that we still have that amount of energy, mg times 4h at the top of the hill and no kinetic, and start from here. And then the car just had enough to make it on down the other side. And when it makes it to where it's about to touch the spring, it has gravitational potential and kinetic. Does that make sense? Because it's still above the reference level, but it's lower than it was, so the amount of gravitational potential it has here has got to be less than the amount of gravitational potential it has there. That remaining energy becomes kinetic. Now, I'm saying this, but we could have also done this problem by resetting the reference level to here. Or we could have done that as well if we wanted. But I don't think you guys are interested in resetting the reference level. I think once you set it, you want it to stay in one place. So that's probably good and makes reasonable sense that you just leave the reference level at one place and don't change it. So to solve this problem, we'll get mg times 3h plus 1/2 mv squared equals mg times 4h. Does that make sense? Do I need to do the arithmetic to find v, or are you guys good with that? Be honest. We're going to subtract this from both sides, giving us 1/2 mv squared equals mgh. We'll probably knock out the m's. Multiply by 2. And then take the square root of both sides. That look good? All right, that's the answer to B. Now, what is the maximum compression of the spring in terms of M, H, K, and any fundamental constants? I don't know why the word maximum is in there. It doesn't make sense. I think we just want what the compression of the spring is. And, well, I see why they use the word maximum, because probably the car is going to hit the spring, come to rest, and then be pushed back out. So we want how far the spring is pushed in, the maximum amount. Okay, I see why they're using that terminology. Again, I think this is an energy question. And the reason is because springs are involved and they're not asking about force. So that makes it sound to me like it's going to be an energy question. The other thing that makes it sound like an energy question is the car has velocity, so we know it has kinetic energy. So again, I think this is an energy question. Now, to do this part of the problem, we're changing things up a little bit. I'm going to get rid of all these things that are in the way. I'm going to realize that the car now is being moved, and it's pushing against the spring until it comes to rest. Is that good? What kind of energy does the car have now?
Elastic.
It has elastic potential energy. Anything else? Gravitational. But that still has to be equal to the mg times 4h that we had before. The total amount of energy has not changed. So I'm going to set this equal to mg times 4h, the amount of energy we had at the top of the hill. So that's going to be 1/2 k delta x squared plus mg times 3h equals mg times 4h. All good so far? All right. Still the same work we did a minute ago, so I'm going to subtract this from both sides and get 1/2 k delta x squared equals mgh. Multiply by 2, divide by k. Is that good? And then take the square root. And look, some of you have some pretty interesting body language here. If this is not good and you say nothing, that's on you. Right? So if you don't know what we did or why we did it, you should speak up. But if you're good, this is what we're doing. To me, this is an adequate test question. Now, I want to talk to you about something here that's important. Are you prepared to talk about something, or are you still writing things down? I'll let you write things down. The spring of spring constant K is located on a landing on the opposite side of the hill. What is the speed of the cart just as it makes it to the spring, assuming it successfully made it over the top of the hill? So when we were doing part B, we were comparing the energy the cart had. Hold on. So the cart's at all these places at different times, right? So when we were looking for the velocity of the cart here, before it hit the spring, right? So this is before it hit the spring. At this instant, right there, when we're at this moment, the cart is above the reference level, so that means it has gravitational potential energy. And it's moving, so it has kinetic energy. Now, that's great and all, but we need to compare this to the amount of energy the cart has, right? To know how much of that energy is kinetic. We know that this, because of how high it is, has to be mg times 3h. But we don't know what this is. We're trying to figure that out. So in order for us to figure out how much kinetic energy it has, I need to compare this with another state of the problem, or compare it with the total amount of energy the car has. Well, I chose to compare it with the amount of energy it had when it was here, because I know it made it to there. So that's why I put in mg times 4h here, because that was how much energy it had at the top of the hill. And I know the total energy, the energy at one place, has to equal the energy at the other. So that's where this 3h came from. And that's why this 4h is here, because I had to take the total energy I have at one place and compare it with the total energy I have somewhere else. Is that okay? Did that answer your question? All right. So here's the thing I do want you to know that's separate from this. Because one of the things I would ask if I was asking this question on a test is I wouldn't ask question B on the test anymore. I would ask question C for sure, which is what we found here. But what I would ask instead is something like, what is the minimum amount I have to pull the spring back in order for the car to make it to the top of the hill? We already have the answer. But that's the question I would ask. That's how I would ask it. So I did this problem in one direction, coming from the bottom of the hill, over the hill, and back to the spring. But what if I wanted to know what is the minimum amount I would pull back the spring to make it to the top of the hill? We already found it. It is this. Because this is how much, when we did this, we were finding how much the spring was compressed if the car had no kinetic energy here and just rolled to the spring, right? If I didn't stop the car at the spring, what would happen? Wouldn't it just go back? Make it right to the very top and just stop? Because it would have no kinetic energy there. So this also represents the minimum amount the spring is going to be pulled back. This is important because in a few minutes we're going to be finding out something else about the spring, aren't we? Have you read all the questions? Because the next part is the important part, the hard part. The next question asks, what is the maximum speed of the cart at the top of the hill so that the cart doesn't go flying off the hill? Right? Doesn't lose contact with the hill? You guys remember that? It even says in the problem, and this is how I know that we're changing what we're doing. It says, this time the cart begins its run from the spring. The spring is pulled back far enough for the car to make it over the hill. The hill, however, is circular with a radius of curvature of h. What is the maximum speed of the cart to successfully make it over the hill and not lose contact with the ground? There is a critical piece of information being given to you there. And if you're not aware of what it is, I'm going to tell you, but it's also changing the problem. This problem is no longer an energy problem by itself. You have to change what you're doing here. And there's a clue as to why. It's a circular track, right? That suddenly becomes a force question. And the reason I know that is because in order to travel in a circle, there has to be a centripetal acceleration. And to have a centripetal acceleration, there has to be an unbalanced force towards the center of that circle. So the moment it said circular track, I knew we were talking about a net force equals MAC problem. I knew it right away. And I know that this has a radius of h. Now, the moment I knew that I was dealing with two forces acting on the car, because it's right there at the top of the track, right? There's got to be a normal force up and weight down. Right? Two forces acting on the car. And we have done this problem before. I'm going to make downwards the positive direction, and I'm going to recognize this is going to involve how fast the car is going. Right? Now, you guys struggle with this stuff all the time. And I don't know how sometimes to reach you about this. So I'm going to try and reach you. God, stop it. I'm going to rewrite this to try and help us, okay? Now, all the things in white are fixtures of the track in the car, right? This is the mass of the car. It's not changing while the car is going along the track. This is gravity. It's not changing as the car is going along the track. H is how big the track is. It's how round the track is. It's not changing. And m, again, the mass of the car. But v can change, right? I can pull the spring back further and make the car go faster, or I can pull the spring back less far and make the car go slower, right? V can change. But if v changes, right? If v changes, n has to change too, because these two things add up to something that's not changing. So if v gets bigger, n has to get smaller. That's the end. In fact, the other side of that works too. If v gets smaller, n has to get bigger. The smallest v can be is 0. Right? That's the smallest it can be. It can be stopped. And if the car is stopped, the weight equals the normal force. Right? We want the maximum speed that it can have and go over the hill. That's got to be when the normal force is 0 and v is at its biggest. Because the normal force can't turn negative. It has to be only positive or 0. So the maximum speed is when the normal force goes to 0, and we get mg equals mv max squared over h. That's how you figure out that velocity. Now, we didn't